How does electrical grounding work in high-voltage systems? Have you ever wondered how electrical grounding works in high-voltage systems? It's a vital aspect of electrical engineering that ensures safety and system stability. Let's break it down in simple terms. Electrical grounding involves connecting parts of an electrical system to the earth. This connection is especially important for the neutral point of transformers or generators. By doing this, we create a stable reference voltage and a safe path for fault currents. This helps protect equipment, stabilize voltages, and keep people safe from electric shock. In high-voltage systems, grounding is critical. High voltages can lead to dangerous situations if not managed correctly. Grounding creates a low-resistance path between the electrical system and the earth. This is essential for preventing overvoltages that could damage equipment or harm individuals. There are several methods of grounding used in high-voltage systems. One common method is solid grounding. Here, the neutral is directly connected to the earth. This keeps the neutral at earth potential, which limits voltage stress on insulation and equipment. It also allows enough ground fault current to flow, enabling protective devices to detect and clear faults quickly. Another method is resistance grounding. In this case, a resistor is placed between the neutral and the earth. This limits the ground fault current to a controlled level, typically around 10 amps or less. This approach reduces damage at the fault point and allows the system to continue operating temporarily without shutting down immediately. Reactance grounding is another option. This method uses inductive reactance in the neutral-to-ground connection to limit fault current and manage transient phenomena. Lastly, there are ungrounded systems. In these systems, there is no intentional grounding, but natural capacitance to the earth may exist. This can lead to higher transient overvoltages and make it harder to detect ground faults. The choice of grounding method depends on balancing safety, equipment protection, fault detection speed, and service continuity. Grounding serves several key functions in high-voltage systems. It stabilizes voltage by connecting the neutral point to the earth, preventing dangerous voltage rises during faults. Grounding also provides a direct path for ground fault currents to flow back to the source. This allows protective relays and circuit breakers to detect faults and disconnect the affected section quickly. Additionally, grounding limits the voltage on equipment insulation during faults, which helps prevent insulation breakdown and equipment damage. For personnel safety, grounding ensures that exposed metal parts of equipment remains at or near earth potential. This reduces the risk of electric shock, which is vital in high-voltage environments. In high-voltage substations and power distribution systems, grounding is implemented through grounding electrodes, such as ground rods or mats. These are connected to the system neutral and equipment frames. The grounding system must have low impedance to ensure effective fault current flow and rapid fault clearing. In complex systems with multiple buildings, grounding and neutral conductors must be properly bonded and interconnected. This maintains a low-resistance return path for fault currents, ensuring that protective devices operate correctly. Overall, electrical grounding in high-voltage systems is a well-planned practice that combines system design, protective device coordination, and grounding hardware. This approach helps maintain system stability, protects equipment, and ensures safety for everyone involved.